discuss why that is so. Particularly, it's actually easier to rationalize why the protein solvents are better for SN1, because the protein solvents can form hydrogen bond effectively with the ions that is being formed. So you start with the neutral species, which when it generates the carbocation becomes polar, and therefore the protein solvent, which is also polar, would help lower the transition state energy for generation of the carbocation, which therefore helps for the SN1 reaction. And in fact, I can give you some numbers for some of the reactions. Let's look at the reaction between the bromide and sodium azide in N3, giving you this product, which is a physical SN2 process. The N3 minus attacks this primary carbon. And displaces the bromine in one state. In this particular reaction, what we see is that if you use water and methanol, it goes extremely slowly. So methanol gives you the relative rate of 1, which when we replace it with water as the solvent, it slightly increases because water is a more polar solvent than methanol. Nevertheless, they are both protein solvent. So the rates are relatively slower, but when we switch to polar protein solvent, DMSO is greater than 1000 relative rate. DMF is almost 3000, and acetonitrile is about 5000. So there's a huge difference. Now, why there is a particular difference between DMF and acetonitrile, we are not going to discuss that. That is actually far more complicated to explain that, how they solve it and how they react with each reaction. It's beyond the scope of this class to discuss that. Nevertheless, you can see that broadly, the polar protein and polar protein solvents, there's a huge difference between them in SN2 reaction, as we claimed in the first statement that polar protein solvent was best for SN2 processes. Now, also in SN1, we see a similar if we do a solvolysis reaction, where you generate carbocation and then you move to the product. Let's look at the reaction of dibutyl chloride with different solvents, essentially, because they would form the carbocation first. So, if we use acetic acid, or for that matter, methanol, in each case now, we get a different product because we are using a different solvent, and ultimately the carbocation reacts with the solvent to give you the product. Okay. And so the last one is water. So in the first case, what we get is the product is this. In the second case, formic acid gives you and the water gives you the alcohol. Okay, so 4 different products are generated in this process. And it looks like when we figure out their relative rates, acetic acid is 1, to methanol is 4 relative rates. Then it jumps to formic acid is about 5,000. And with water, it's 150,000. So there's again a huge difference from this, where we used agents that are, essentially these are all protein solvents, polar protein solvents, but the dielectric constant of acetic acid is about 6. Methanol is 33. Formic acid is 58. And water is 78, which is the highest dielectric constant of all the solvents that we normally discuss. And so there is a clear-cut difference. There is, of course, a cutoff line. Methanol, I would expect it to be higher, but it wasn't. And it's still very low, and then it jumps when we go to formic acid, which is from 30 to 58 is the dielectric constant. So there is a light cutoff line somewhere in the 40s where the rate really jumps. And again, that discussion is beyond our time here, but it gives you the general impression of how these reactions may be influenced by the solvent. All right, so we also discussed the effect of competition between the SN1 and E1 versus SN2 and E2. The SN2 and E2 reactions are particularly well suited to manipulate depending on the type of reagents that you use. So if we have a primary substrate, let's say CH3, as I mentioned before, this being a primary carbon, if we use a sodium ethoxide, then it's likely to undergo mostly substitution, okay, this being the primary carbon. So it would be mostly substitution, giving you plus NADR. I'm not writing that. So this would be greater than 90%, and there would be some 10% of the elimination product. However, as soon as you switch it to the secondary carbon, and use the same reagent, and again, this is an ethanol. We use the same reagent, now it switches to the substitution product being the minor product. This is about 10%, and the elimination product is 9%. Now, you can also manipulate this reaction by changing the agent, because rather than using a secondary base, you can use a tertiary base, which is more hindered, and you can switch this reaction to predominantly elimination. So you can use the same substrate, but you can force this reaction to go mostly elimination by using potassium tertiary butoxide. And this is again tertiary butanol. Now elimination is predominant. And that's because the agent itself cannot attack very efficiently, even though the carbon is primary, because itself is so hindered, it is preferably would pull up a proton and carry out the elimination reaction. So these are essentially the competition between E2 SN2 reactions. And obviously, if your agent is mostly a nucleophile and a weak base, then you would expect to see up to the secondary, predominantly the SN2 rock. Yes.
In that final reaction, if you had changed the reagent, the reaction to the tertiary compound from the reaction prior to it, would you see a difference in the rate?
Okay. Repeat the question. The tertiary
Yeah.
butoxide that I used.
So I mean the first reactant there, CH3, GTR.
Right.
Yeah, if you change that to the molecule compound above it,
The second one, which is the 2-butanol.
yes.
Right? So 2-propanol. 2-propanol, if you switch the first one, that's what I did in the second one, right?
Yeah, I mean, if you make that a tertiary bromide, would you then see more go to the substitution reaction than you see there right now?
Okay, I still don't understand your question. You're saying that if I switch this one with this, right?
The last one,
Or the last one.
yeah, with the one right above it.
Oh yeah, that's already, even with the sodium ethoxide, it's predominantly elimination. And it would be almost exclusively elimination if we have both the secondary substrate and the tertiary agent. Yeah, it would be almost 100% elimination product. Yeah. All right, so the SN2 and E2 are therefore competitive process, but it allows you to manipulate the reaction. SN1 and E1 are also competition, but that really depends on a variety of factors. It's less controllable. Because you generate the carbocation in the middle, and then if you have a solvent that is relatively small and that is a weaker base, then of course you get more substitution product. But the manipulations are actually more stringent and more difficult to do in this case. But it still can be done, and we'll later see some examples of that when we'll try some of the problems. Okay, let me move on to something else. We mentioned the leaving group ability. And that plays a critical role in some of these reactions. Because you, of course, want a good leaving group. Otherwise, the reaction is not going to happen. Always, for example, in a very now, if you want to carry out an nucleophilic reaction with anything like a good nucleophile, let's say, there will be no reaction. And why that is so? Because the nucleophile is attacking this carbon. There's no problem with that. But the leaving group is so poor, it cannot just leave. It cannot break the bond between carbon and oxygen. It's a poor leaving group. And also we have seen that, in fact, if you use the halogens, there is a clear distinction between the type of halogen that we use. So let's assume that you have used now, depending on the type of halogen that's there, you will get the product, but the rates would be significantly different from one another. And in this case, okay, I minus is far superior than Br minus, which in turn is Cl minus, and F doesn't work very well. F is a little better than OH, but nevertheless it's not very good either. So there is a clear-cut effect of the leaving group there. And frequently what also happens is that you need to have a really good leaving group. And what is often done is, particularly if you have an alcohol, you can convert it to a sulfonate. So the sulfonates are excellent leaving groups. And particularly the sulfonates have a general formula of R this is sulfonic acid. And so you generate a derivative of OSO2. So the derivative that is generated is now depending on the R group also, the rate could be actually vary significantly from one another. The R typically we use is CH3, which is called mesylate, a methyl sulfonic acid. So this is you can have most common is para-toluene sulfonic acid. And there's also trifluoromethyl, so C3 is the trifluoromethyl sulfonic acid. These three are commonly used, but the more common one is this one, okay, the para-toluene sulfonic acid. So in other words, let's say if you have an alcohol, such as the first one that we use, in order to make the OH a better leaving group, what you can do is treat it with the corresponding sulfonyl chloride. So let's say para-toluene is the one you selected. So use the corresponding chloride, and so the OH can attack the sulfur and displacing the chlorine, generate the corresponding so this is the ester that is being formed. And we frequently abbreviate that. This part is 4 years. And therefore, this formula can be written as an abbreviated form CH3, CH2, choose almost any nucleophile, it's going to attack this. Okay, sodium cyanide, for example, that's going to attack and displace this and make the corresponding cyanide. And if we compare the rate of this leaving group, typically we see the following differences between them. So it's starting from chlorine, Cl minus to CF3, SO3 minus. There's a millionfold difference in their rate of release. Okay, starting from 1 to 10 to 100, then the mesylate, this is what it's called. These are all three are different groups, but more frequently we use the paratonic. This one is actually so touchy that a little bit of change in condition, it just living group falls apart. Okay. That's why it's more difficult to handle and more frequent to use the OTS. This is the abbreviation again. The paratonic company as living group. Okay. So there's a huge difference in the living group. Yes. It's 1 million, right? 1 to 1 million. So these are some of the effects of the living group that we see, and this is therefore a very effective way to use OH groups to make a good living group. And another advantage of using that oscillate or one of the sulfonyl chloride living group is that they would maintain the stereochemistry of the way the OH is added. So if you have a situation where, let's say, if you have a specific stereochemistry, as in this case, this is a compound which is R, and you convert it to the tosylate, which is also going to be maintaining the R stereochemistry because the chiral carbon is not affected. So the OH will be converted by using paratonic sulfonyl chloride. To make the So we convert it to the tosylate with exactly the same stereochemistry. Still maintains the R stereochemistry. And now you carry out the SN2 reaction with anything, you will end up getting, let's say, if you use cyanide, going to get an inversion of configuration where you are going to get converted to gas stereochemistry. So that's why this is particularly useful to manipulate the stereochemistry of chiral compounds. Any question? All right, so I'm going to go over the self-test that I handed out to go over some of these problems from this year. So in this case, let's first identify the type of reaction that is happening in the first question. Okay, so what we need to do is to figure out what kind of carbon is being attacked, and also what kind of reagent you have. So the first case, we identify this is the carbon. Right? So this carbon is primary, right? And therefore, the primary carbon, and what you have is a good nucleophile, good base. But because the carbon is primary, as we have given the last example, it's going to undergo mostly as SN2 substitution. So this is SN2 process. And you know the product. All right. The second one is using sodium cyanide as the reagent and forming this. And because it's a good nucleophile, we would assume that the starting material will have something that has a good living. You can make an iodide or bromide. And so in this case, we also need to know that the cyanide carbon, this is undergone an inversion of configuration. So what we started with should be this. If we consider its iodide, then this would be I. This would be the starting material that would react with cyanide to make this. The next problem is 1-chloro-3-methylbutane with sodium iodide in acetone. So you have a chloride, in other words, the 1-chloro is right Cl. This is 1, 2, 3, 4. And 3-methyl, another methyl group here. In sodium iodide again, we see that this is a primary carbon. So this is a fairly straightforward. Again, you will convert that to iodide. Okay, I should replace this here. The next one is where there is a change of mechanism, because now you have secondary carbon. This is secondary. And you use sodium methoxide, which is a good nucleophile group base. And now it's going to undergo mostly, because it's secondary carbon, mostly it would be elimination rather than substitution. It would be E2. So the major product would be an E2 product, a minor product would be an SN2 product. This one again is SN2 process. Sodium azide. Azide is a good nucleophile, and you have a good living group, Br, but it's going to attack from this side. The incoming group would be axial. Next one is also SN2 reaction. Br is a good leaving group. S minus methyl is going to attack this carbon, and therefore it's going to undergo an inversion of configuration. Here, a hydrogen, and it's coming from the other side, therefore SCH3 dropped like this. Okay. Next problem is you have two leaving groups, but Br is far better than fluorine, and therefore the thiol, SH minus, is going to attack this carbon, and that's where the inversion of configuration will happen. So Fischer rejection allows you to, this one remains intact, HF, and so the SH will come here, and hydrogen will go there. Right? Next problem asks you to choose the best pair of reactants to form the following ether by an SN2 reaction. So you have two different choices. You can cut it here or here. And so let's see which one we would like to do. So this one can react with the O minus, and you have the leaving group here. And the other one will have so leaving group, let's call it Br. It could be anything, but group rho 1. Okay, so you have two different options. And in the first option, we see that the O minus is attacking the secondary carbon. Okay. Therefore, there is a problem. It is going to undergo mostly elimination. The second option is this O minus is attacking a primary carbon, which is perfect. So we'll rule out this one. This is the better way to make it. Question 3 asks you to outline the chemical step necessary to convert, okay, this compound, which has a tosylate, excellent leaving group, to the cyanide, except that they are maintaining the same steady group. Therefore, you need to have double inversion in order to negate the same steady group. Otherwise, you undergo inversion configuration first. So initially, if you start from this one, let's convert it to another one. So we use, let's say, a bromide. So NaBr. That would cause an inversion of configuration. And then we use the cyanide to do a double inversion, giving you the same retention of configuration. S2 pentanol to R, this one. So S2 pentanol is okay, so we have a hydrogen and an OH group here, right? The 2-pentanol, this is the 2 position. And if we write the OH here, that would be actually R, therefore we'll say switch that. This is H. So this is S2-pentanol, and in order to convert it to R, the ideal method would be convert this to tosylate, and then we'll carry out the attack by the SCH3 minus. So let's do tosyl chloride, TSCl, abbreviated. And for this, we usually use little bit of pyridine because you exact same stereochemistry, OTS. Okay, and then you carry out a reaction with SCH3 minus. That is going to attack from the other side, and you'll have a complete inversion of configuration. Right? You know what the structure is. That will be R. Okay. Question 4. Hydrolysis of 3-chloro 2,2-dimethylbutane yields 2,3-dimethyl-2-butanol as the major product. Explain this observation using structural formulas to outline the mechanism of this reaction. All right, so let's write the structure of 3-chloro 2,2-dimethylbutane. 3-chloro-2-dimethyl. Okay, so this is the compound that we started with. Sorry, rewrite that. Three-chloro. Dimethyl butane. So this is the compound we start with, and sorry, what did I? 3, 1. Sorry. Rewrite this. Getting hung up with the nomenclature. Okay, so this is that 2,2-dimethyl 3-chloro-butane. And that goes to the product which is 2,3-dimethyl-2-butanol. Butanol. All right, so this is essentially the conversion that took place, right? You start from this compound, okay, which is, let's say, 2,2-dimethyl 3-chloro-butane, and then it goes after the reaction with it goes to, let's say, with H2O or any other solvent like that. It would go to the 2-butanol, but the methyl group, you have 1, 2, 3, 4, 5 carbon unit. It's also 1, 2, 3, 4, 5 carbon units. All right. So in order to carry out this reaction, what you see would happen is dimethyl butyrol, correct. 1, 2, 3, 4, 8. So we start with this compound. So the very first step is breaking the bond and forming the carbon cation. So that would therefore generate this carbon cation, which is secondary. And therefore the next step, what you would expect, is one of the methyl group migrate to here, giving you this other cation, which is tertiary. And therefore, in the next step, H2O can react with the carbon cation, which can then react with another molecule of water, giving you the corresponding alcohol. So this is therefore a typical mechanism that we expect with carbon cation formation and rearrangement of that, right? Okay, going back to the other problem. Identify the class of reaction such as E2 and write the kinetics and chemical equation for the sulfolysis of t-butyl bromide and methanol. So we expect the t-butyl bromide to undergo methanol. There's no good nucleophile. Therefore, that is going to generate t-butyl carbon cation, which then undergoes the sulfolysis, which is therefore a process of SN1. SN1. Therefore, we are going to see the rate as K times the bromide, t-butyl bromide. Only. The reaction of chlorocyclohexane with sodium azide, this is now an SN2 process, and therefore the rate would include both of them. It would include the chlorocyclohexane plus the N3 minus. Both of them are indicated in the rate expression. Provide a brief explanation of why the halogen exchange reaction shown is an acceptable synthesis. Okay. I minus is a better nucleophile than Br minus, and it's a reasonable leaving group. So this is going to attack and displace the Br in SN2 process. And one advantage of that is that sodium bromide is less soluble than sodium iodide in acetone. And therefore this is going to precipitate. And as a result, removed from the solution. So following the La Chatelier's principle, we are going to see that the more reaction would generate each time the bromide drops, then this pushes the reaction from left to right. Briefly explain why the reaction of 1-bromobutane with sodium azide occurs faster in DMSO than in water. Okay. And again, this is what we discussed before, that this is a reaction of SN2 process, okay, because you have good nucleophile and good leaving group, bromine, and therefore in SN2, the polar electronic solvent such as DMSO is better than water. Write chemical structures for compound A through D in the following sequence of reaction. And this type of problem, you are better off starting from the end. At the end, we see that you can again cut off the ether, either here or here. And again, using the same analogy to the previous problem that we did, you are better off having a bromine on the primary carbon. So B and D should likely be, one of them would be like an ethyl bromide. The other one would be the alkoxide, O minus N plus. So this one attacks very efficiently on the primary carbon, generating this product. So these two are B and D, and because you used HBr, C must be therefore, this must be D, and C therefore would be CH3, CH2OH, which forms D after HBr and E, and therefore A would be, because you're using sodium amide, which therefore forms the sodium salt, this would be the corresponding alcohol. That would be A. Right? Write a mechanism describing the solubilisis of 1-bromo-1-methyl cyclohexanate ethanol. Again, you don't have a good nucleophile, and it's also a tertiary carbon. Therefore, you expect to form a tertiary carbocation in the first step, which therefore generates the CH3 plus in the first step. In the second step, you would expect that ethanol to attack and form this, which reacts with another molecule of ethanol, giving you the final product. So that would be the expected step-by-step thing that happens. All right. And the last problem here, solubilisis of the compound shown after 3-carbocation rearrangement. What you expect to see here that it's going to generate a carbocation here. Which is secondary, and therefore you expect it can be primary, it will be tertiary if we remove the hydride from here. So that carbocation will form there. Okay? And then that will be